Okay, welcome back. Happy Wednesday, everybody. Today is September 14, class number 4. We are back in chapter 2. We are covering 2.2, which is the derivative at a point. And if you have some calculus experience, then you probably have seen that word derivative before. It is a word that we are going to be using nearly every single day for the rest of the semester. It is fundamental to what we are about this semester. Thank you for your enthusiasm. That's great. Okay, a couple of pieces of business before we jump in. Number one, as we find our routine, our rhythm here this semester, you can see I'm walking around checking homework. When I'm checking your homework, it's a great time to ask me, hey, I couldn't quite figure out how to do this part or this question, and we're getting some people just a little bit of a hint, and that's oftentimes enough. Before class is also a great time to ask those same homework questions of your neighbors, because almost certainly with the collective knowledge of everybody here, we've got all the homework done. Like at least one person knows how to do each problem in the homework. So ask around, and I'm happy to help if I can. Before we jump in, and again, we are on page 17, so get your big packets open to 17. I just want to spend a couple of minutes talking about the arbitration project. This is the first project. You might want to take the project out if you happen to have it handy. We're going to jump in on page 9 of the reading. The page number is on the top right. So the project number 1, if you have it handy, go ahead and take it out. It's okay if you don't have it with you. And we're starting on page 9 of the reading. So first, just want to be clear, again, on the back of the first page, it's got this recommended timeline. Today is class number 4, so if you are on track according to this timeline, then you have finished reading pages 7 through 9 and also 9 through 11, and you have finished exercises 1 and 2A and 2B. There are only 7 exercises here, but what's going to get you is the reading. The reading is challenging. It's going to push you. But in any event, I think I've tried to space this thing out pretty well. So if you are on track, you have finished reading up to page 11 and done questions 1, as well as 2A and 2B. Now, I know that some of us have been working really hard on this project. I suspect some of us have not opened this project. And to those who haven't opened it yet, what I'm about to say is not going to give you very much help because you haven't read anything yet. But if you are in that category, maybe do some reading later on and then come back and check out this video on YouTube. So let's just take a quick look at the stuff on the top of page 9. And actually not at the top, we're going to jump down a little bit here. Let's jump to the bottom of page 9. So we've got this collection of numbers, so just to make sure everybody's on the same page, we've got these 2 people, Ellen and Frank, and they have a vacation they're going to take together, and their 3 choices for where they go are the beach and the mountains and staying home, which is a perfectly good option, right? So SQ is our abbreviation for status quo. So status quo means stay home, B, go to the beach, M, go to the mountains. There's a lot of notation in this little 2-line thing down here. U, what does U stand for? Utility. U is a utility function, which I'm guessing most or all of us have never heard of before we read this thing. It was true for me. I had never heard of it until I read this thing myself. And so the top row has U sub E, U sub E, U sub E. This top row is Ellen's utility function. Now, I'm going to use a different word besides utility. So what the paper is calling utility, now utility is just a measure of usefulness. And in this case, we're talking about going on a vacation. And so if I'm trying to measure how useful a vacation is, to me, I'm thinking of it in terms of happiness. So that is my translation. Utility here is happiness. How happy is it going to make you to go to the beach? How happy is it going to make you to go to the mountains? And how happy will you be if you stay home? And I like to have units, and I'm just going to make up some units for happiness. I'm going to call them hearts. The more hearts I have, the happier I am, okay? And so just looking at Ellen's utility function, let's start over here. Ellen going to the mountains. She gets 3 hearts worth of happiness if she goes to the mountains. She'd be quite happy going to the mountains, okay? Ellen staying home, 0 hearts. It is neutral. She's not happy, she's not unhappy. It's just the status quo, business as usual. And in fact, by the time we get to this part in the reading, we have moved everybody's status quo to 0 hearts. We're gonna scale everybody so that everybody staying home, we're gonna call that a 0, even if they didn't call it a 0 initially. And then what does this mean right here? That's right. If Ellen has to go to the beach, she is going to be -1 hearts unhappy. She would prefer to stay home than to go to the beach. After all, you get sunburn, there's jellyfish on the sand. There's lots of reasons Ellen doesn't like going to the beach, okay? Yeah. All right, same business down here. We can interpret Frank's numbers just in terms of hearts. If Frank gets to go to the beach, what happens? 7 hearts. Oh my goodness, he's just tickled to go to the beach. Frank staying home? 0. He is neutral, and we have moved everybody, so they're neutral staying home. But if you make Frank go to the mountains, he is going to be unhappy. -1 heart's worth of unhappiness. Okay. On the very next page, we take this information and we graph it. So I'm looking at the bottom of page 10 now. And so it's really important to keep track of what's going on here. This point right here does not represent Ellen per se. It does not represent Frank per se. What does it represent? It represents the mountains. It represents what happens to both of our people if we go to the mountains. This is the point 3 and -1. Ellen's utility is on the horizontal axis. That means 3 hearts for Ellen if she gets to go to the mountains. It means -1 heart for Frank if you force him to go to the mountains, okay? So we're taking the information in the previous page, which was split up into a row for Ellen and a row for Frank, and we are merging it together to make information about a trip to the mountains. How will they both feel if they both go to the mountains? Same kind of idea up here. This point B up here says at the beach, -1 heart for Ellen, and is that a 7? 7 hearts for Frank. Okay, so what are our options in terms of our vacation? There are only 3 of them. You can stay home, you can go to the mountains, or you can go to the beach. Going to the mountains favors which person? Ellen, but poor Frank is desperately unhappy. Going to the beach favors which person? Frank, but poor Ellen is desperately unhappy. Status quo is neutral. Neither party is unhappy or happy. So we've only got 3 choices, but how about we do something a little bit more interesting than just pick one of these options, which either makes one person unhappy or it's just the status quo and we might as well not play this game at all. How about we have a lottery? How about we flip a coin? Half the time we go to the beach, half the time we go to the mountains. Or how about we roll the die? And a third of the time we go to the beach, and a third of the time we go to the mountains, and a third of the time we stay home, right? There are different possibilities here. And our job is to try to find the best lottery, the most fair lottery that is somehow going to maximize the overall happiness for both parties involved, Frank and Ellen, okay? That's what this project is about, is pick the lottery that's going to maximize the overall happiness, whatever that means. Okay, if you were to say flip a coin, half the time beach, half the time mountains. That corresponds to a point that is between the beach and the mountains, exactly halfway. I'm just going to ballpark it and say it's right there. So this would be like half beach, half mountains, never staying home. Okay? Now, it is not possible for us to halfway go to the beach or halfway go to the mountains. That's not what we're saying. But we're flipping a coin, letting chance decide which one we do. If we were to go to the beach, again, Frank's happiness is a 7. But we're only going to the beach half of the time, right? So how about on average, we just take half of that 7 and say, well, if Frank gets to go to the beach half the time, then on average, he's going to get 3.5 hearts for these trips to the beach, right? 3.5, half of the 7. And let's continue to look at Frank. If we go to the mountains, half the time, Frank gets a -1 heart because we've gone to the mountains. And so half of that -1 is just a -0.5 hearts. And so here's what I'm envisioning. Half of the 7 hearts for going to the, which one, beach, plus half of the -1 heart for forcing Frank to go to the mountains. Altogether, what is this equal to? I think that's a 3. So what that means is if we were to flip this coin, say hundreds of times, and take hundreds of vacations, half of them will be to the beach and half of them will be to the mountains, probably pretty close to that. On average, Frank can expect to get 3 hearts out of this deal. He'll never get 3 hearts on any one trip, right? He can't get 3 hearts on a trip. He can either get 7 or -1. But on average, if we let these guys do this experiment lots and lots of times, he will end up on average with 3 hearts. And so that's like his expected outcome for this particular lottery where it's a half and a half. But there's lots of other lotteries that you could pick. And this 3 hearts has completely ignored poor Ellen, so we should probably do the same calculation for Ellen, and you're going to be doing these kinds of calculations in the early parts of this project. Does this make sense? Any questions on any of this? Okay, so hopefully that there's a little bit of a push that will kind of make some of this abstraction a little more concrete. It's not just numbers you're playing around with. Just imagine hearts and these folks' happiness. Okay, so let us jump to the big packet, page 17 here. And we're just going to do a very quick review of something we did 2 classes ago. You guys will recall there was a problem where we were dropping, I think it was a ball off of the CN Tower in Canada. And this purple curve here was the height of the ball as a function of the time that had passed. And we were really interested in finding the instantaneous velocity at t equals 5 seconds. That's what we wanted to find. That was a big part of this activity. And so what did we do? Well, we took the distance, we took the point at 5 seconds and we fixed it. And then we took this other point here, it was green, and we found the slope of what's the line connecting the 2 points on the curve? Secant line. And the slope of that secant line wasn't instantaneous velocity, it was average velocity between 5 and wherever this green point was. And then we took this green point and moved it closer and closer and closer to the fixed point at 5. Secant line turned into tangent line, and that was our definition for instantaneous velocity at t equals 5 seconds. And you'll recall that one way we had to do this was to define h to be how far it is between the fixed point and the varying point, how far horizontally it is. And so that made this point over here, what was this point? It was a 5, but now we're moving h over to the right, comma, and then the function evaluated at the same 5 plus h, whatever that thing is. And so if we want to calculate the slope connecting the 2 points, the red 5, 327.5, and then this new orange one over here, we get slope equals, all right, so it's just s of 5 plus h minus s of 5. It happened to be 327.5, but I'm going to leave it as s of 5 divided by 5 plus h minus 5. And that is just the change in distance over change in time. Remember doing this? Yeah, Ben.
Where does the 5 plus 8?
The 5, all right, so 5 is the number we're focused on, this dot up here that's fixed. And then we're just going to call h some arbitrary amount that we're going to move horizontally. Yeah. And what are we going to do with h in order to get these 2 points on top of each other? Yeah, we're going to make h closer and closer to 0, right? Okay, so that calculation right there in blue hopefully looks familiar. That's how we did average velocity. On the bottom, the 5s cancel, and no matter what number it is, they're both going to cancel. And so we get this kind of pattern here. Okay, so let's move on to the material for today. See if we can find this thing here. It looks like this. Page 27. Our daily summary. In this class, we define the derivative as the slope of a tangent line. We also extend instantaneous velocity to more general instantaneous rate of change. Number 1, everything we've done with velocities over the last few classes can be applied to arbitrary functions, not just to height or distance function. For a general function, the average velocity becomes average rate of change, and instantaneous velocity becomes instantaneous rate of change. So I'm just going to rewrite the thing that I had written on the previous page. It was this divided by, and then canceling those 5s, we just get an h downstairs. And we said that the way to take that varying point and shove it right on top of the fixed point was to send h to 0. So that's our instantaneous velocity at 5. We can change it so that it's not an S function. S typically stands for height or position. We can just make it a generic F, any old function, not necessarily related to movement. And then the 5 can be any old number. It is A in this case. Notice that the two A's are the same there. Those are the 5s. And then the H is just H, and we always send H to 0. Okay? So that right there is I'll highlight it here. That right there is the instantaneous rate of change at a particular number A. And so we're going to see an example now of an instantaneous rate of change that has nothing to do with movement or falling or anything like that. So let's try number 2 from your textbook. The population f of t of China in billions of people can be approximated by f of t equals 1.267 times 1.007 to the t, where t is the number of years since the start of 2000. So the output of this function is population, billions of people, okay? So part A, what kind of a function? We're looking for a math word here. Is this guy? That's an exponential function. So the letters that you use depend on the book you're talking about, but a times b to the t is sort of our standard definition for an exponential. Number times a number to the variable. Part B, does this function represent exponential growth or exponential decay? It's growth because, yeah, it's bigger than 1, that base, right? So it is growth because the base, which is 1.007, is greater than 1. So we are growing. Population of China is growing in this model. Part C, what is the growth rate written as a percentage? It's 0.7%. It's just the excess of this purple number, this 1.007. Just how much bigger than that? How much bigger is that than 1? It is 0.007, which we can write as 0.7%. So what that says is that the population of China is growing by 0.7% per year. Okay. Now we answer the harder question. Part D, what is the growth rate at the start of 2015 as an absolute amount? Said another way, estimate how fast the population was growing at the start of 2015. But the growth rate is constant. It is 0.7%. But the number of people that you gain every year is changing, right? In the year 2000, when the population is the smallest, you're going to gain, I don't know how many people in a year, but then 15 years later, you're going to gain more people in that year, even though it's the same 0.7%, because you are taking 0.7% of a bigger starting population in 2015 than 2000. So let's give this a shot. We are going to use our magic formula right here. It is highlighted in yellow. Let's go for it here. Limit as h approaches 0, f of, okay, the only thing that we're going to change from that yellow formula to what we're writing here is the a. How much is the a in this problem? It's the value we're focused on. It's not the 0.7%. It's not that either. A is the input, which is the value of t in this case, and 15 is the value that we need. 15, h is always there, 15 plus h minus f of 15 divided by h, because this problem is focused on the moment 2015, and that's a. Everything else is just copied, right? So the only thing that you do when you use this formula is pick the right value of a. Okay, so now we got some algebra to do. Equals, copy limit h goes to 0. F of 15 plus h. Okay, I will highlight up here in green. There's our f formula. We're about to change the t to what? 15 plus h. That's what we're doing. So we copy all that stuff in green. 1.267, 1.0007. Nope, too many zeros. To the what? 15 plus h. That's it. Minus. And now we're doing f of 15, and we just change the t to 15. So 1.267, 1.007 to the 15, all divide by h. Okay, this is a limit. Every time I see a brand new limit, I just try plugging the thing in. So in this case, I'm changing h to what number? 0, and just see what happens. Okay, so if you change h to 0, right up here, this becomes 15, right? 15 plus nothing. And so what happens on the top when you do this subtraction? You get 0. That just completely cancel. And on the bottom, again, we're picking h equals 0, and we get 0. And so we get 0 over 0, which is very common and unfortunately means there's work to do. And that's always what we're going to get when we do this calculation. Okay, so we're going to use the calculator. Remember, we had a couple of options last class. You don't need to type this in right now. But we had a couple of options last class. You can look at a graph or your table of values, or maybe just maybe algebra. We can't do algebra on this guy. So really all we have is the graph and the table of values. Okay, so I'm just going to type in all of that stuff. 1.267 times 1.007 to the, okay, so 15 plus. Now I'm not going to put h here. I'm going to put a number. But remember, we're sending h to 0. So how about we do something like 0.1? Some number close to 0, minus 1.267 times 1.007 to the 15th power. Close parentheses, divided by h. What is h here? 0.1 is the h that I picked. Now, it's kind of annoying to type that whole thing in one fell swoop. Far easier would be to calculate this guy separate from this guy. But it is very dangerous to do that, because if the calculator runs out of space on the screen, then no matter how many digits you write, you are rounding. And in this case, we're talking about billions of people per year, and a little bit of rounding in like the third digit might be like millions of people different than the right answer. And so it's important for us to be able to type in and get as much accuracy as the calculator can give. Okay, so this right here, let's think about the units. What are the units on top? Billions of people. What are the units on the bottom? Yeah, remember it came from like a 5 plus h minus 5. So they were the units of the input variable. In this case, the input variable is time measured in years. So the top is billions of people. The bottom is years. So this number right here is 0.0098 billions of people per year. That's the increase in China's population from the year 2015 to the year 2015.1. We're just looking at a tiny, right, like a tenth of a year. So billions of people per year, but just looking at that little tenth of a year interval. How can we get a better approximation here? Let's try 0.01, and we'll do the same thing up here. Second insert will allow me to just put in 10. Let me hit enter. Are these numbers exactly the same? Nope, but they're not too far apart, and gives me some hope that, yeah, maybe we're going to hone in on some number. Let's just do one more calculation here. We'll do 0.01 and then insert one more 0. And again, not exactly the same, but more digits agree in these two numbers than the previous two numbers. And so let's just go ahead and write down as many digits as we feel like of this thing right here. That's our answer. If you want to put another 0, you get a slightly better answer. Not expecting a nice number here. It's just, it is what it is. Okay, so how about we just record that from the calculator. Grab it here. Okay, so this is our answer here. And so we'll get some units on this guy too. So approximately 0.0098 billions of people per year. I think this problem said let's answer in millions of people. So what is that? 9.8 millions of people per year. Questions on that? Okay, part E says estimate how fast the population was growing at the start of 2000. It's almost exactly the same problem. All we're changing is what to what. Change 15 to, for the year 2000, 0, right? Because we were going years from 2000. Okay, so we're just going to kind of jump to the punchline here. Where is it? I'm just going to leave this most accurate answer with the 0.001 in it, and I'll just change my 15s to zeros. So 0 there, and delete, and then change the other 15 to a 0, and delete. And we get about how many millions of people per year? About 8.8. Does it make sense that it was growing slower in 2000? Yeah, because it was a smaller population to start with. So about 8.8 million people per year. So approximately 8.8 millions of people per year. And I just want to highlight, I know we're doing some big old calculation here, and the calculator is kind of burying, it's hiding a lot of the work that's going on. But all we were given in this problem was the population function. Nothing about the way the population was changing. All you have is lots of information about like snapshots. If you plug in 0 into our population function, it tells you the population in the year 2000. Plug in 15, tells you the population in the year 2015. You can plug in any number you want, but you are not getting any kind of sense just by plugging a single number in. You don't get a sense of the way the population is changing. But here we do. Right? We're taking like the height function, turning it into a velocity. We're taking the population function and in a real sense finding the velocity of the population in China. How fast is it growing? Okay, next page, number 3. That calculation that we just did with the limit is called the derivative of the function f at x equals a. In our case, we found the derivative of the population function at 15 and also at 0. Note the independent variable will usually be x, so we'll generally use x instead of t. It's just lots of notation. Here's real important notation. It is denoted by f with a little apostrophe of a, and that's read f prime of a. So you see that little apostrophe, you're just going to change it to the word prime. So the derivative of f at x equals a is given by this whole crazy thing. The right-hand side of the equals we saw on the previous page. The left-hand side is just our brand new notation, and we're going to use it over and over this semester. F prime of a. Number 4, just some vocabulary. Finding the derivative of a function is known as differentiating the function. If a function has a derivative, the function is called differentiable. All of these phrases are important, and they will hopefully become second nature to you soon enough. Number 5, as we've seen, the average rate of change of a function, which is the thing in the parentheses, which is the same as our highlighted thing, except what's missing is the limit, right? So if we just do the average rate of change, not the instantaneous rate of change, which is with that limit, the average rate of change is the slope of a secant line. And as we've seen, as h goes to 0, what does the secant line become? Tangent line. Okay, quick look at a Geometer Sketchpad file. I've got it open here. This function, this parabola-looking thing, is that f of x is equal to pi times x squared. So just a parabola with a little vertical stretch in it. I've got 2 points here. One of them is called the special point. The other one, anybody know this word? What is a lemming? Yeah, it's a little animal. It's a rodent. And what are lemmings known for? They just follow. Like you got this whole trail of lemmings, and one of them walks off a cliff, and they all just walk off the same cliff. It doesn't matter that it's real. It was a great part of my childhood with a video game I used to play. So here's the idea. So we've got the special point. At the moment, the special point is at x equals 2, and the slope of this secant line is negative 11.2. But if I move this if I move this lemming point to closer and closer to follow that special point, then the secant line, as we said, becomes a tangent line. And the slope of that tangent line in this case is about 12.6, and that is the derivative. So at x equals 2. The derivative, which is just the slope of the tangent line, is about 12.6. If I were to take the special point and move it up here, let's say somewhere around there, do you think the derivative is smaller or bigger here than it was a moment ago? It's bigger because the tangent line is going to get steeper. And so we'll move the lemming over to the special point. The derivative over here, I forgot, was it 26, I think? 26, or maybe it was 16, I don't remember. It definitely wasn't as big as it is here. That's a 37. If I were to take the special point and move it to the origin, what is the derivative there? 0, because the tangent line is flat. And so all these secant lines, like I really like the fact that there's this visual like movement happening, because literally what we do is we take a secant line, which is something you could have done a couple of algebra classes ago, and you turn it into the tangent line. You move it to the tangent line. In this case, the slope is really close to 0. It should be exactly 0. I didn't quite hit the origin there. And one more point, if I take my special point and I move it over here, let's go there. What kind of a derivative will this point have? Something negative. And negative pretty big because it's pretty steep out here. And so we move the lemming to follow the special point, and we get some pretty steep negative tangent line. Okay, so coming back here, number 7, this next statement is super important. The derivative of a function at a point is the slope of the tangent line of the function at that point. So we're going to just sort of chant rhythmically. Ready? I'm going to read the stuff in light. You're going to read the stuff in bold. We need all participants here. Here's the Cliff Notes version. The derivative is the slope of the tangent line. In case you missed it, the derivative is the slope of the tangent line. I'm not hearing from you. We got to get nice and loud. Last one. One more time with feeling. Oh, you lost your voice. The derivative is the slope of the tangent line. Really, really important for us. Yes, good. Okay, see how far you can get here. Raise a flag if you get stuck.